Every year, over 4 billion tons of concrete are produced worldwide, more than any other man-made material. But few people know that it can be made significantly stronger, more environmentally friendly, and even cheaper, with the help of dust from ancient volcanoes. Volcanic ash, a natural gift that can replace up to half of the cement, reducing carbon emissions by hundreds of pounds for every ton. How exactly does ash that once fell from the sky turn into concrete that can last for centuries? Watch until the end, because at the end, you'll learn a secret that could change the perception of construction. Depending on the type of concrete and specific requirements, volcanic ash can replace from 10% to 50% of Portland cement by weight. On average, many projects use a replacement of about 20 or 30%. Our journey begins in quarries, where we extract high-quality volcanic ash. This natural material, left after ancient volcanic eruptions, is a key ingredient in our concrete. First, large excavators load the raw volcanic ash into dump trucks, which deliver it to our processing plant. Here, the ash undergoes primary processing. It is crushed to the desired particle size and sifted to remove any large impurities. This stage is extremely important for ensuring the uniformity and quality of the final product. We use specialized crushers and screens that allow us to obtain a fine powder, which provides optimal reactivity in the concrete mixture. After crushing, the ash is stored in large silos, ready for use. At this stage, we also conduct strict quality control, taking ash samples for analysis in our laboratory. We check its chemical composition, specific surface area, and density to ensure it meets our high standards. Each batch of ash must pass a series of tests before being approved for further processing. This allows us to guarantee the stable quality of our concrete. After preparation, the volcanic ash is transported to a central mixer, where it is combined with other key ingredients: cement, water, and sand and gravel. The mixing process is carefully controlled by a computer system to achieve the perfect consistency. Here, volcanic ash acts as a pozzolanic additive, which improves the properties of the concrete, making it stronger and more durable. The ratio of ingredients is determined by our engineers and depends on the specific requirements for the concrete. For example, for concrete that will be used in aggressive environments, we add a larger amount of volcanic ash to increase its resistance to sulfates and other chemicals. Water is supplied through dispensers that accurately measure its quantity to ensure the optimal water-cement ratio. This ratio is critically important for the strength and workability of the concrete. Additionally, we may use various chemical admixtures, such as plasticizers or hardening accelerators, to modify the properties of the concrete. These additives allow us to adapt the concrete to different construction conditions. For example, to ensure rapid setting in cold weather, or to increase its fluidity for easy placement. Cement production is an extremely energy-intensive process. The use of volcanic ash, which is a natural material and does not require intensive thermal processing, significantly reduces the overall energy consumption in concrete production. This can lead to an energy reduction of 20% compared to traditional concrete. After thorough mixing, the liquid concrete is fed to the forming lines. Depending on the final product, we use different forming methods: casting in molds, vibropressing, or extrusion. These machines are automated and provide high precision and production speed. For example, for the production of concrete blocks, we use vibropresses, which compact the concrete mixture under high pressure and vibration, creating strong and uniform blocks. For the production of slabs, we use molds into which the concrete is poured, and then it is compacted using vibrating tables. These molds can be of different sizes and configurations, allowing us to produce a wide range of concrete products, from small landscape design elements to large building structures. An important part of this stage is also reinforcement, if it is necessary for certain products. Steel reinforcement is inserted into the molds before the concrete is poured, which significantly increases the strength and load-bearing capacity of the final product. The entire process is controlled by operators who monitor the operation of the equipment and the quality of the finished products. Volcanic ash significantly improves the resistance of concrete to sulfate attacks, chloride corrosion, and alkali-silica reaction. Sulfate resistance can increase by up to 50%, and the reduction in chloride permeability by up to 70%. This makes it ideal for marine structures, roads with high salt use, and wastewater treatment plants. After forming, the concrete products are moved to curing chambers. This is a critical stage where the concrete gains its final strength. In these chambers, optimal temperature and humidity are maintained, which promotes the hydration of cement and volcanic ash. The curing process can last from several hours to several days, depending on the type of concrete and strength requirements. After curing, each product undergoes strict quality control. Our specialists check its dimensions, shape, and surface for defects. Samples are also taken for testing for compressive strength, bending strength, and frost resistance in our laboratory. We adhere to the highest quality standards to ensure that every product manufactured at our plant meets or exceeds our customers' expectations. Each concrete sample is subjected to a series of tests to ensure that it can withstand the declared loads and operating conditions. This includes tests for tensile strength, water impermeability, and resistance to aggressive environments. We also conduct non-destructive testing using ultrasonic and X-ray methods to detect hidden defects. After successfully passing quality control, the finished concrete products are transported to warehouses, where they are stored until shipment. The production of 1 ton of Portland cement generates approximately 2,000 pounds of carbon. By replacing 25% of the cement with volcanic ash, we can reduce carbon emissions from concrete production by 250 pounds for every ton of cement produced, or by 60 pounds for every cubic yard of concrete. Concrete with volcanic ash is used in a wide range of construction projects: bridges, roads, dams, tunnels, where high strength and durability are required. It is estimated that 20 to 30% of infrastructure projects in regions with available volcanic ash could effectively use this material. Foundations, walls, floor slabs, where strength and environmental friendliness are important. For example, in geothermal projects, where resistance to high temperatures and aggressive fluids is required. Not all volcanic ash is the same. Its properties vary significantly depending on the source and geological history. The ash can come from different igneous rocks, such as rhyolite, andesite, and basalt. Each type has a different chemical composition, meaning the content of silica, aluminum, and iron, which affects its pozzolanic activity and color. Finer ash usually has a larger specific surface area, which provides a faster and more effective pozzolanic reaction. However, particles that are too fine can increase the water demand, so a balance is needed. The quality of volcanic ash largely depends on the content of the amorphous phase. It is this phase that is the most reactive. Crystalline components are less active. We carefully analyze this indicator in our laboratory. In addition to functional advantages, concrete with volcanic ash can offer interesting aesthetic possibilities. Depending on the chemical composition of the source, volcanic ash can give concrete different shades of gray, brown, or even black. This can eliminate the need for painting or allow for the creation of unique aesthetic effects. For example, ash with a high iron content can produce warmer tones. Thanks to the fine particles of ash, the surface of the concrete can be smoother and more uniform, which is valued in architectural concrete and decorative elements. Imagine, glass that once shattered into deadly sharp fragments now saves lives. How did humanity transform a fragile substance into armor for a car? And what is hidden behind this seemingly simple transparency? Every year, over 100 million square meters of automotive glass are produced worldwide, enough to cover the area of an entire country. But the real magic happens where molten stone is transformed into a perfectly smooth surface, in furnaces that reach temperatures of over 2,700 degrees Fahrenheit. How did ordinary quartz sand become the foundation of safety technology, without which we cannot imagine modern transport? Watch until the end, and you will learn what accidental experiment changed the history of automobiles forever. The history of automotive glass production is closely linked to the development of the automotive industry, which emerged at the end of the 19th century. The glass used in cars today has come a long way in improvements. making it safer, stronger, and more functional. When the first cars began to appear, they were initially not equipped with glass at all. The open body design only partially protected passengers, and dust, wind, insects, and other hazards made trips very uncomfortable. Later, as cars became faster, the need to install protection for the driver and passengers arose. The windshield began to be made from ordinary window glass, which, although it provided some protection, had a serious drawback. During accidents, it shattered into large, sharp fragments, leading to numerous injuries. The first revolutionary discovery in the field of automotive glass was the creation of laminated glass. This happened by chance. In 1903, the French chemist Edouard Benedictus accidentally dropped a flask with a nitrocellulose coating. The glass cracked but remained whole thanks to a thin layer of plastic. This accident inspired the scientist to create multi-layered glass, which later became the basis for triplex. Already in the 1910s, laminated glass began to be used in premium class cars. Its construction consisted of 2 layers of glass, between which a thin, transparent film was placed. In the event of an impact, the glass did not shatter, and the cracks remained on the film. In the 1920s, laminated glass began to be actively used in the production of windshields. Its main advantage was increased safety. Even during serious accidents, the fragments did not fly apart, but remained in the polymer layer. The next stage in the development of automotive glass came in the 1930s, when the technology for producing tempered glass was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it broke, it disintegrated into small pieces with blunt edges, which minimized injuries. In the mid-20th century, tempered glass began to be used for the side and rear windows of cars. It was cheaper to produce compared to triplex and provided a sufficient level of safety for these parts of the car. In the 1950s and 60s, automotive glass became even more perfect thanks to the development of technology. During this time, various important changes took place. Improvement of triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production. The automation of production processes allowed for a reduction in the cost of automotive glass, which made it more accessible to the mass market. Sun protection coatings. For the first time, special coatings began to be used that blocked ultraviolet light and reduced the heating of the car's interior. One of the most important technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, allowed for the production of perfectly smooth glass by spreading the liquid glass mass over the surface of molten tin. Thanks to this method, glass became more uniform, strong, and accessible for mass production. The float method is still the basis of automotive glass production today, ensuring its precise dimensions, surface smoothness, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 1960s, heating filaments began to be installed in the rear windows of cars, which prevented fogging and freezing of the glass. In the 1980s, glass with special metal coatings appeared, which reflected sunlight and reduced the heating of the interior. Glass with ultraviolet protection. Thanks to the introduction of new technologies, automotive glass began to provide almost complete protection against harmful radiation. And then we begin the modern period of automotive glass production, which we will talk about now. And we will start with glass for cars. Automotive glass is divided into several types depending on its purpose and production technology. Windshield. Usually this is multi-layered glass, which consists of 2 layers of glass, between which a polymer film is located. Such a design ensures that upon damage, the glass does not fly into sharp fragments. Side and rear glass. Most often this is tempered glass, which upon impact breaks into small blunt-angled pieces, which reduces the risk of injury. Panoramic roofs, or other special types of glass. Laminated or tempered glass with a special coating for protection against ultraviolet radiation is often used. The main components of glass are natural materials that are mixed in certain proportions to obtain the desired properties. Quartz sand is the main component of glass, which ensures its transparency. It must be extremely clean and contain a minimum of impurities. Soda is added to lower the melting temperature of the glass. Lime improves the mechanical stability and chemical properties of the glass. Additional additives used to correct color, transparency, resistance to ultraviolet light, and other properties. The raw material is cleaned, dried, and crushed to a uniform state. It is important that impurities that can affect the quality of the glass are maximally eliminated. After preparing the raw material, it is loaded into special furnaces for melting. This stage includes several important moments. Let's look at them together. Melting temperature. A temperature of about 2,732 degrees Fahrenheit is used to form the glass mass. In the melting process, the raw material turns into a uniform viscous liquid. Homogenization. The glass mass is mixed for an even distribution of components. This is important to avoid air bubbles or inhomogeneities in the finished product. Furnaces for melting glass are equipped with modern temperature control systems and process automation, which ensures high quality of the final product. After melting, the glass mass undergoes a forming process, which in modern production is most often performed using the float method technology. Feeding the glass mass, the liquid glass flows out of the furnace and onto a bath of molten tin. Thanks to the high density of tin, the glass mass spreads evenly over its surface. Under the influence of its own weight, the glass forms a perfectly even and smooth surface. By gradually lowering the temperature, the glass acquires hardness. At the exit of the bath, it can already be processed. The float method allows for the production of glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions required for automotive production. Automated cutting machines ensure the accuracy of the work. To prevent the formation of cracks and chips, the edges of the glass are ground. Each sheet is checked for defects, such as microcracks, bubbles, or other damage. Next, to ensure the strength and safety of automotive glass, it is subjected to a tempering process. The glass is heated to a temperature of about 1,112 degrees Fahrenheit. Then, the surface of the glass is rapidly cooled by streams of air, while the inner layers cool more slowly. As a result, stress is created, which increases impact resistance. Tempered glass, when destroyed, breaks into small, safe fragments, which minimizes the risk of injury. Next, for the windshield, triplex is used, a construction of glass and polymer film. Its production includes several stages. Joining the layers. A polymer film is placed between two glass sheets. The construction is placed in a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to a temperature of 284 Fahrenheit under high pressure. This ensures a strong connection of the layers. Triplex has high impact resistance, and upon damage, it remains in the polymer film, which ensures the safety of the driver and passengers. Next, to improve the properties of automotive glass, various coatings are applied to it. Anti-reflective coatings reduce glare from the sun or headlights of other cars. Ultraviolet protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings ensure that water runs off the surface of the glass. Heating elements. Thin heating filaments can be embedded in the windshield, which facilitate the removal of ice or fogging. To achieve the desired shape, special thermoforming installations are used. The glass is heated to a temperature at which it becomes plastic and is formed according to the given parameters. And so, we have reached the final stage. During it, each product undergoes a thorough check. Transparency and the presence of defects are checked. Next, the glass is tested for impact resistance and endurance to loads. Compliance with standards. The accuracy of dimensions, shape, and other parameters are checked. Then the finished automotive glass is packaged in such a way as to avoid damage during transportation. It is delivered to car factories or service centers, where it is installed in vehicles. The production of automotive glass is a high-tech process that combines physics, chemistry, and engineering. Thanks to modern technologies and strict quality control standards, automotive glass ensures safety, comfort, and durability. And just imagine how many stages the automotive glass had to go through for us to be able to monitor safety on the road and have the opportunity to admire the wonderful landscapes. It seems incredible to me. And you? Every year, over 900,000 aircraft engines are manufactured worldwide, hearts that push giants of the sky on journeys across continents. But have you ever wondered how this metal monster is born? One that operates in conditions of over 2,000 degrees and at speeds that could destroy any metal. Inside it, titanium bones, a nickel heart, and composite lungs. And then, technologies resembling alchemy, single crystals, vacuum casting, and 3D metal printing. But the main secret is not in how it's created, but what's hidden inside. Watch until the end, and you'll learn something that even Boeing engineers keep quiet about. The turbofan engines that push giants of the sky, like Boeing and Airbus planes, resemble something out of science fiction. However, they are a true embodiment of engineering genius. How are these amazing machines assembled from tens of thousands of parts and ingredients, like a puzzle? Ordinary metals are not suitable for their manufacture. After all, the engine must operate in conditions where the temperature can exceed 1,800 degrees Fahrenheit. This is a real inferno, and ordinary steel simply wouldn't withstand it. This is where titanium alloys come on stage. Lightweight, strong, and able to not melt in extreme heat. And for the hottest zones of the engine, nickel-based superalloys are used. By the way, this isn't just metal, it's 21st century alchemy. Composites, particularly carbon fibers, are used for the fan to reduce weight while maintaining strength. Such a high temperature arises from the process of burning fuel in the combustion chamber, one of the most important elements of a turbofan engine. During engine operation, aviation fuel, usually jet fuel, is mixed with air and ignites, forming hot gases. These gases are literally accelerated to insane speeds and temperatures, over 1,800 degrees Fahrenheit, and sometimes even up to 2,700 in modern engines. This level of heat is needed to get the most efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that spins the turbine and provides the aircraft's motion. And here lies the main challenge. The engine must not only withstand these extreme conditions, but also operate stably, without the slightest failure. That's why it uses super technological materials, like titanium alloys and special composites, which can withstand both high temperature and insane mechanical stress. You know what's incredible about the process of creating an engine? That even individual parts, like the turbine blades, are created with micron precision. For example, the blades are cast in a vacuum so that there isn't even the smallest crack inside. Some of them are formed to have a single crystal structure. That's when a piece of metal has no seams at all. But that's not all. 3D printing? Yes, that's used too. For example, for complex parts that are impossible to make with traditional casting. The turbine blades are the heart of the engine. They operate in the hottest zone and convert the energy of the hot gases into rotational motion. First, a model of the blade is created from wax. Yes, it looks almost like artistic sculpting, only here, precision down to the micron is important. This wax sample is then dipped into a special ceramic solution, which gradually dries, forming a strong mold. This mold is like a perfect cast of the future blade. The wax inside is melted and removed, and the ceramic is ready for the most important stage. Next, the show begins. In a special furnace, superalloys are melted, which include nickel, chromium, and other metals capable of withstanding temperatures above 2,000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But the secret is not only in the material, but also in the way it's done. To make the blade withstand gigantic temperatures and loads, it is often cast as a single crystal. This means that the entire piece of metal has no seams, micro cracks, or different grains, as in ordinary metal. Why is this important? Seams or micro cracks in such conditions are like a minefield. One mistake, and the blade shatters. Single crystals are grown through very slow cooling. The mold with the molten metal is gradually lowered into the cooling zone of the furnace. This process can take several days, but the result is a perfectly strong and durable blade. When the metal cools, the ceramic mold is broken, and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface so that it can withstand extreme temperatures even longer. And so, each blade is checked separately. If there is even the slightest defect, it doesn't go any further. Fuel injection nozzles, combustion chamber parts, or even compressor blades in aviation are made using 3D printing. For example, the company GE Aviation prints nozzles for its engines that weigh 25% less, but are 5 times stronger than traditional ones. Layer by layer, from powder and light, parts are created that allow planes to fly faster, farther, and more economically. First, engineers create a digital 3D model of the part with maximum precision. Here, every curved surface or cavity matters. Why? Because these parts often work in places where a millimeter can change everything, from the engine's efficiency to its reliability. The digital model becomes a map for the 3D printer, which knows where and how to create the required shape. Instead of the usual piece of metal, an ultrafine powder is used here. For example, of titanium, nickel, or Inconel, this is a super aluminum alloy. It looks like sand, but with particles so fine that they are almost invisible to the naked eye. The powder is poured into a special reservoir, and it becomes the building material. The principle of the printer's operation is simple but ingenious. It melts the powder using a laser or an electron beam. The laser heats the powder to such a temperature that it literally fuses into a homogeneous metal structure. Then the next layer of powder is applied, and the process is repeated. This method is called selective laser sintering or melting. And what's cool is that 3D printing allows for the creation of even the most complex geometric shapes. For example, parts with internal cooling channels, which are generally impossible to produce by casting or milling. You know, in traditional manufacturing, you often have to first make a large part and then cut off all the excess. This is not only time-consuming, but also expensive because a lot of material is wasted. But 3D printing works differently. Only what is needed is created without waste. The resulting part is not yet completely ready. After printing, it undergoes heat treatment. It is heated and gradually cooled to relieve internal stresses in the metal. Then comes the final grinding, polishing, or mechanical processing if precision needs to be adjusted. And of course, each part undergoes thorough testing. After all, everything here is serious. If a part does not withstand the load, the consequences can be catastrophic. The engine assembly takes place in a huge hangar, where every foot of space is occupied by tools, engine parts, and people in overalls who are intently working on something extraordinary. This place is the final stage of creating an aircraft engine. Here, individual parts, such as blades, compressors, combustion chambers, and casings, are transformed into a single whole, ready to lift an airplane into the sky. It all starts with the engine casing, which resembles a giant metal cylinder. This is the skeleton to which all other parts will be attached. The casing is made of titanium or nickel alloys, as it will have to withstand insane loads. Engineers work like watchmakers, The casing is secured in a huge machine tool to ensure everything is perfectly level. Next come the compressors, several rows of blades that are responsible for compressing the air before it is fed into the combustion chamber. The blades are installed one by one, as if decorating a giant wheel. Each one is checked by hand, as the slightest defect can ruin the entire job. After the compressors, it's the turbine's turn. These are the blades that convert the energy of hot gases into motion. The turbines are placed so precisely that the distance between the blades and the casing walls is sometimes measured in microns. Next, the combustion chamber is installed, the real hell of the engine. Here, compressed air is mixed with fuel and burned. Engineers install special nozzles that ensure a uniform fuel supply. And here, everything must be perfect. An incorrect nozzle angle, and the engine can lose efficiency or even fail. A central shaft runs through the entire engine, a kind of backbone. At one end of the shaft, a fan in the form of a huge wheel is attached to the front of the engine. At the other end, the turbine. When the turbine rotates under the influence of hot gases, the shaft transmits this energy to the fan, which sucks in air. Special robots are used to install the shaft. This part of the process requires surgical precision, as even a microscopic misalignment can cause vibrations that will kill the engine. When the internal part of the engine is assembled, the external systems are added. Fuel pipes that supply fuel to the combustion chamber, an oil system that provides lubrication for all moving parts, and electronics because the engine is literally packed with sensors that monitor temperature, pressure, speed, and much more. These elements are attached using cables, tubes, and bolts that must withstand not only vibration, but also extreme temperatures. After the assembly is complete, the engine is not sent to the aircraft right away. First, it is attached to a test stand, where real flight conditions are simulated, from takeoff to turbulence at an altitude of almost 33,000 feet. This is the most spectacular stage. Starting the engine at full power is accompanied by a roar that can be heard for several miles and bright gas streams. The engine runs under load for hours, and engineers check it for strength, endurance, and efficiency. When the engine passes all tests, it is disassembled, the main components are checked again, and then it is finally assembled. The finished engine is packaged and transported to a Boeing or Airbus factory, where it becomes part of a new aircraft. And so, part by part, engineers create the heart of an airplane, which is capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Let me know if you would like to see more videos like this. Every year, over 50 million tons of batteries are discarded worldwide, from small AA batteries to giant electric vehicle batteries. Imagine a mountain of metal reaching the size of Mount Everest, filled with toxic substances. But now, part of this mountain gets a second life. Behind the thick walls of factories, old batteries are put into shredders where steel blades tear them apart. They are frozen with liquid nitrogen and turned into a black powder that will once again become lithium or cobalt. Watch until the end. You will see how a new future for energy is born from waste. Battery collection starts with people. Private individuals turn in batteries from phones and laptops. Car service centers, batteries from electric vehicles, and also businesses that use a lot of equipment. Collection points are in electronics stores, supermarkets, or specialized collection centers. Here, everything is as manual as possible. People bring batteries, and staff or volunteers accept and record them. Old batteries from factories or car service centers are delivered by trucks to large collection centers. Special battery containers have sensors that determine the fill level. When a container is almost full, a signal is sent to the collection company. Some companies use drones to check the fill level of large containers in remote locations. Batteries are sorted by type by people and machines, because batteries come in different types: lithium-ion, nickel metal hydride, lead acid, and so on. They cannot be mixed during recycling. At small collection points, for example, in cities, batteries are sorted manually by workers. They rely on markings, labels, and appearance such as shape and case color. Small batteries from smartphones or laptops go in one direction, and large batteries from electric vehicles in another. At large enterprises, automatic sorting lines are in operation. Machines scan batteries by size, weight, and the type of metals they contain. X-ray analysis or spectroscopy is used to determine exactly which battery is in front of the machine. After scanning, the batteries move along a conveyor to different bins, where they await the next stage. Even at automated factories, people are present. Operators check whether the machines are sorting the batteries correctly. If a problem arises, for example, a torn battery case or a missing label, people intervene and sort manually. Batteries from electric vehicles or solar stations are too large for automatic lines. This is where robots come into play, helping to disassemble these giant blocks into smaller sections. Then they are sorted by material. No matter how much machines do, people are still the most important in the sorting process. These are mainly the workers at collection points and the operators of sorting lines. Specialists assess damaged batteries manually because machines cannot yet recognize all defects. Machines work faster, but for now, they can't do without people. Ultimately, every correctly sorted battery is a chance to recover rare earth metals and reduce environmental harm. Next, the batteries need to be shredded. They enter real metal jaws. The batteries are loaded into a machine that looks like a huge shredder, equipped with steel blades. The blades are so powerful that they can even shred the body of an electric car. Metal chaos ensues. The sound of tearing, grinding, and cracking. The batteries are literally ripped to shreds. Since the batteries can be charged, they first undergo freezing in liquid nitrogen. This cools the metals and reduces the risk of ignition. Some shredders operate in sealed chambers with inert gases to exclude contact with oxygen. There is also a more spectacular option. In some places, a controlled current is first used for ignition. The battery literally burns out, leaving only the metals. The batteries are shredded into pieces from a few centimeters to a crumb, depending on the type of shredder. The blades rotate at a speed of over 2,000 revolutions per minute, and metal fragments fly in all directions with a clang inside a protected chamber. The shredded pieces pass through magnetic separators, which with filigree precision extract ferromagnetic metals, for example, nickel or cobalt. Fragments of other materials continue their journey along the conveyor. A fine black powder, known as black mass, settles in special containers. This is where the treasures are hidden: lithium, cobalt, manganese. Machines literally suck up the powder with dust collectors to gather even the microparticles. Residues that are not suitable for recycling, meaning plastic and traces of electrolytes, are washed away with special streams of liquid. At this stage, hydraulic crushers are used, which turn the remnants into a slurry that is easy to filter. Engineers monitor the condition of the shredders and the temperature level inside the chambers. Specialists work with the results of the shredding. They check whether all the metals have been separated and whether any extra impurities remain. If a battery is charged and has defects, it can literally explode during shredding. But the system controls this. The explosion is extinguished by gases, and the process does not stop. After the batteries are shredded and that precious black powder is obtained, science in action, as they say, begins. The metals that seem to be hidden forever are extracted using two main methods: hydrometallurgy and pyrometallurgy. And although this may sound a bit technical, the processes themselves are extremely interesting. So what does it look like? Battery fragments are immersed in special acid solutions. There are huge tanks where a yellowish-green liquid is bubbling. This could be sulfuric or hydrochloric acid. During immersion, a reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve in this soup. To extract the desired metal, a clever trick is used: ion extraction. Special reagents, for example, organic compounds, are added to the liquid, which capture a specific metal, like a magnet. As a result, each metal settles into a separate layer. When the metals are separated, they are precipitated in the form of salts or hydroxides. They look like small white or colored crystals. For example, lithium precipitates as lithium carbonate, a powder that looks like fine sugar. Cobalt becomes a bright blue precipitate, and nickel, a pale green one. If hydrometallurgy is a gentle approach, then pyrometallurgy is more like shock therapy for metals. Here, everything literally burns and melts. The black mass is loaded into a huge arc furnace, where the temperature reaches almost 3,000 degrees Fahrenheit. The metals melt into a liquid mass, and the plastic and other residues simply burn up. The metals stratify like oil and water, but at the temperature of molten lava. Several layers form in the furnace. Heavy metals, meaning cobalt and nickel, settle to the bottom, while lithium remains in the slag. This is the upper, lighter layer. Then this slag is broken up and processed separately to extract the lithium. After cooling, the metals take the form of small ingots, shiny, smooth, and ready for reuse. The cooling after the pyrometallurgical process usually happens in a controlled manner. After all, if you just let the molten metals cool on their own, it could take hours and sometimes even days. In addition, such cooling can create an uneven metal structure. This will affect the quality of the final product. Therefore, they are usually cooled in special chambers, where the cooling rate can be regulated. If the controlled cooling is air-based, the ingots are left on a conveyor under powerful fans. It's like a giant hairdryer that quickly cools the metal surface. If it's water cooling, for a faster process, the metal ingots can be immersed in a bath of water or special liquids. This is a huge tank where the red-hot ingot, upon entering the water, releases clouds of steam. It looks quite spectacular. Sometimes there is combined cooling. This is when some stages begin with air cooling and then are completed with water cooling to reduce stress in the metal. Controlled cooling ensures a uniform structure of the metals, which is critically important for their reuse in batteries. This reduces cracks or defects that can arise from sharp temperature changes. The obtained lithium is used to create new batteries, those that will charge electric cars or even your phones. Nickel can become part of turbines that generate energy from wind, and cobalt, an important component of medical equipment. So we are literally closing the loop. Old batteries give life to new technologies. Discarded batteries can turn into a real environmental disaster. First, they contain toxic substances that pollute the soil and water. Second, the mining of new rare earth metals not only depletes natural resources, but also harms the environment. Recycling solves both of these problems. You know what else is cool? The more batteries we recycle, the less we depend on mining new materials. This is a direct path to sustainable development. Despite the popularity of lithium, only 1% of this metal is currently recycled. The main reason is the high cost and complexity of the process. But researchers are developing new technologies that could change the situation in the coming years. Interestingly, even now, electric car manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to maintain control over valuable materials. Every year, humanity creates energy that on one hand saves cities, and on the other, hides an incredible story of transformations. One average reactor produces 1,000 megawatts and requires only 27 tons of enriched uranium per year, the weight of 3 school buses. But to get these 27 tons, you have to mine and process over 100,000 tons of ore. In this video, we will follow the path from a noisy mine and acid vats to supersonic centrifuges, furnaces, and tiny fuel pellets. Every step is chemistry, giant machines, and unexpected risks that you are almost never told about. Stay until the end, and I will reveal one secret to you that will change your perception of atomic energy. An average American nuclear reactor has a capacity of about 1,000 megawatts. For it to operate for 1 year, it needs approximately 27 tons of enriched uranium fuel. 27 tons is the weight of about 3 school buses. And now let's compare. To produce the same amount of electricity, a coal-fired power plant needs to burn over 3 million tons of coal. That's over 10 million barrels of oil. Nuclear fuel is the highest form of energy concentration that humanity has ever created. But to get these 27 tons of fuel, you need to start with a much, much larger amount of raw material. The chain of transformations is simply staggering. To produce those same 27 tons of enriched uranium fuel, you need to start with 215 tons of uranium concentrate. And to get those 215 tons of concentrate, you need to mine and process over 100,000 tons of uranium ore. Imagine a giant mountain of stone, the size of a multi-story building, which ultimately turns into a volume of fuel that fits in one truck. This shows how dispersed uranium is in nature and how complex the process of its concentration is. It all begins in the roaring chaos of a uranium mine. Imagine a deep shaft or a giant open-pit quarry, where huge machines with a deafening roar bite into the rock. The air here is thick with dust, and every stone that is brought to the surface looks absolutely ordinary, just a gray, dull granite or sandstone. The uranium here is invisible. It is dispersed in the rock in the form of tiny microscopic inclusions, and its concentration is incredibly low, often less than 1%. This means that to get 1 pound of uranium, you need to mine and process hundreds or even thousands of pounds of barren rock. Dump trucks, loaded to the brim, take this ore to a nearby processing plant that hums. The first stop is the primary crusher. This is a giant steel maw that, with a deafening crunch, crushes large stone blocks into pieces the size of a fist. Then, this crushed stone goes by conveyor to a huge mill. A giant rotating drum, filled with steel balls, resembles an industrial washing machine for stones. Here, in a continuous roar, the ore is ground into the finest grey sand, almost dust. And now the real chemistry begins, a process called leaching. This grey sand is mixed with water, forming a thick pulp, and pumped into huge vats, the size of a small house. A powerful chemical solvent is added to these vats, most often sulfuric acid. This acid, like a hungry predator, begins to eat the uranium, pulling it out of the solid rock and turning it into a liquid, dissolved state. This process lasts for many hours, while the entire mixture is continuously stirred. As a result, we get two things. On one hand, tons of wet, now unnecessary sand, so-called tailings, which are toxic waste, and on the other, a murky, greenish-yellow liquid containing our precious uranium. This liquid needs to be cleaned and concentrated. It is passed through a series of columns filled with special ion exchange resins. Imagine this as a high-tech water filter. The resins, like a magnet, pull out only the uranium ions from the solution, letting everything else pass by. Then these resins are washed with another solution, which washes the concentrated uranium off them. And so, finally, our final product is precipitated from this clean, saturated liquid. By adding ammonia or hydrogen peroxide, the uranium is forced to fall out of the solution in the form of a bright yellow, thick precipitate. This precipitate is filtered, dried in furnaces, and at the output, we get the same famous yellow cake, a heavy, radioactive, mustard-like powder. This is the uranium oxide concentrate, the first step on the long path to clean energy. The next step is purification to an absolute, almost unearthly purity. The yellow cake is sent to a special plant, where it is dissolved and, with the help of complex chemical processes, such as solvent extraction, all impurities are removed from it. The goal is to obtain perfectly pure uranium dioxide. But here the main problem arises, which is at the heart of all nuclear energy. In this perfectly pure uranium, 99.3% is the stable, lazy isotope uranium-238, which cannot sustain a chain reaction. And only 0.7% is the energetic, unstable isotope uranium-235, which is our fuel. They are chemical twins, and it is impossible to separate them by chemistry. To make the reactor work, we need to increase the concentration of this energetic uranium-235 from 0.7% to 3 or 5%. To begin enrichment, the solid uranium must be converted into a gas. It is treated with hydrofluoric acid, turning it into uranium tetrafluoride, and then with fluorine to obtain uranium hexafluoride. This is a very corrosive and dangerous compound, which has a unique property. It becomes a gas at a temperature slightly above room temperature, and so this gas, packed in special containers, is sent to an enrichment plant. Imagine a giant, noisy workshop the size of several football fields, filled with thousands of identical, tall, metal column-like devices. These are gas centrifuges. Each of them is a high-tech top that rotates at supersonic speed, making tens of thousands of revolutions per minute. When our uranium gas is pumped inside, the magic of physics begins. The heavier gas molecules with uranium-238, under the action of centrifugal force, are pressed against the walls of the centrifuge, and the very slightly lighter molecules with uranium-235 remain closer to the center. This is a microscopic difference, but it is enough. Special tubes take the gas from the center, which now contains a little more uranium-235, and send it to the next centrifuge in the cascade. And the depleted gas from the walls is diverted to the side. To achieve the required concentration of 3 or 5%, the gas must pass through thousands of such centrifuges. This is an incredibly long and energy-intensive process. When we have finally obtained our uranium hexafluoride, enriched to the required level, it needs to be converted back into a solid material suitable for fuel. With the help of chemical reactions, it is turned into a black powder of uranium dioxide. But this is not just any powder. Each of its particles has a perfectly calibrated size and shape. Now the most interesting part begins, the creation of fuel pellets. This black, heavy powder is sent to a press. Imagine a high-precision pharmaceutical press, only instead of medicine, it stamps radioactive pellets. It compresses the powder with incredible force, turning it into small, dense, perfectly cylindrical granules, or pellets. They are still brittle, like chalk. To give them strength, they are sent to a furnace. But this is not an ordinary furnace. This is a high-temperature furnace, filled with hydrogen to prevent oxidation. There, at a temperature of over 3,000 degrees Fahrenheit, these pellets are baked for many hours. During this process, called sintering, the powder particles fuse together, and the pellet turns into an extremely hard, dense, ceramic-like substance. It becomes so strong that it can withstand the extreme temperatures and pressures inside a nuclear reactor. Each pellet after this undergoes laser control, which checks its dimensions with micron accuracy. The next step is assembly. These small black ceramic candies are carefully, one by one, loaded into long, thin tubes. These tubes, about 13 feet long, are not made of steel, but of a special zirconium alloy called zircaloy. This material is unique in that it is very strong, resistant to corrosion, and most importantly, almost transparent to neutrons, allowing the chain reaction to proceed without hindrance. When the tube is completely filled with pellets, it is filled with an inert gas, usually helium, to improve heat transfer, and hermetically sealed at both ends. Now, it is not just a tube with pellets, it is a fuel element. And the final stage is the creation of a fuel assembly. Several hundred such ready-made fuel elements, for example 17 by 17, which gives a total of 289 pieces, are assembled into one large square bundle. They are held together by special spacer grids. This ready-made assembly, which looks like a giant, high-tech quiver with arrows, is the final product. It weighs about half a ton and is ready for shipment to a nuclear power plant. And so, having passed an incredibly long and complex path from an ordinary stone through chemical transformations, supersonic rotation in centrifuges, infernal baking, and precise, almost clockwork assembly, this concentrated bundle of energy is born, ready to quietly and reliably produce millions of kilowatts of clean electricity for several years. Imagine this. In the heart of the ocean depths, or in the roar of an airplane turbine, there is a part that decides everything. A single shaft, capable of transmitting the power of 1,000 Ferraris, or withstanding speeds of over 10,000 revolutions per minute. But how is this steel axis, which can lift a space shuttle, born from an ordinary cold ingot? And what do a ship's propeller, the size of a 3-story building, and the precision of a jeweler, removing a few grams of metal, have in common? In this video, we will reveal the secret of creating giants, without which neither a ship nor an airplane can move. Watch until the end. A fact that will turn your understanding of the power of metal upside down awaits you. A shaft is a steel rod that transmits colossal power from the engine to the propeller. You can't just take any steel for it. Giant, perfectly clean steel ingots, each weighing tens or even hundreds of tons, are brought to the factory. This is not scrap. It is a special vacuum degassed alloy from which almost all impurities have been removed. This massive cold cylinder is first sent to a furnace. But this is not a melting furnace. This is a giant heating chamber where, for many hours and sometimes days, the ingot is slowly and uniformly heated to a temperature of about 1,200 degrees Fahrenheit. It becomes dazzlingly yellow, plastic like clay, ready to meet the hammer. And so begins the most brutal and ancient art of metallurgists: forging. A giant crane picks up the red-hot ingot and places it under a hydraulic press hammer. This is a monster capable of dropping its top with a force of tens of thousands of tons, with a deafening, deep boom that makes the ground tremble. The hammer slowly but relentlessly descends onto the red-hot metal. These are not quick strikes. This is a slow, methodical squeezing. After each strike, a manipulator slightly turns the ingot. And so, strike after strike, hour after hour, the formless cylinder begins to stretch and take the shape of the future shaft. This process does not just change the shape, it does something incredible inside the metal. It compacts its crystalline structure and aligns all the grains of steel in one direction, along the axis of the shaft. It's like turning a scattered pile of straws into a tightly twisted rope. A shaft born in a forge will be many times stronger and more resistant to torsion than a simply cast one. After the forge, we have a rough, black, scale-covered blank that only vaguely resembles a shaft. It's time for the sculptor. It is secured in a giant lathe. Imagine a lathe half a football field long. The blank begins to rotate slowly, and a cutter of super hard alloy is brought to it. With a hiss and a screech, it begins to remove layer after layer, turning the black, uneven surface into a perfectly smooth and shiny one. A continuous ribbon of hot, bluish metal shavings, resembling a streamer, comes off the cutter. This process lasts for many days. Computer control ensures accuracy to the hundredths of a millimeter over the entire 30-meter length. Some shafts are made hollow to reduce weight. For this, a perfectly straight hole is drilled through its entire length. After final grinding, the surface of the shaft becomes as smooth as a mirror. Now that the spine is ready, it's time to create its heart, the propeller. This is a completely different story. A propeller has an extremely complex, aero or hydrodynamic shape that cannot be forged. Therefore, it is born from liquid fire, by casting. The main material for marine propellers is not steel, but a special bronze. It is slightly less strong, but it is not afraid of corrosion in salty seawater. First, engineers create a perfect computer model of the propeller. Then, based on this model, an exact full-scale copy is carved from wood or foam. This model is a true work of art. Next, this giant model, which can be as tall as a 3-story building, is buried in a huge pit filled with special molding sand. The sand is carefully compacted around the model, creating a perfect impression of its shape. Then the mold is disassembled, the model is removed, and we are left with a cavity inside the sandstone that exactly repeats the shape of the future propeller. This is our casting mold. Meanwhile, in a giant induction furnace, tons of bronze are being melted. It turns into a liquid, dazzling gold, boiling at a temperature of 1,800 degrees. A huge ladle brings this river of molten sun to our mold. And the foundry workers, dressed in silvery fire-resistant suits, slowly and carefully, through special channels, begin to pour the metal into the sand mold. This is a tense and dangerous moment. The metal must fill every smallest curve of the mold, leaving no air bubbles. After pouring, a long cooling process begins, which can last for weeks. When the metal has finally solidified, the moment of birth arrives. With a roar and clouds of dust, the sand mold is broken, and our propeller is revealed to the world. It is still ugly, black, with a rough surface. It is sent for processing. First, the remnants of metal from the gating system are cut off, and then it enters the maw of a giant 5-axis milling machine. A huge milling cutter, controlled by a computer, for hours, layer by layer, removes the excess metal from the blades, giving them a perfectly precise, calculated aerohydrodynamic shape. But even after the machine, the surface is not perfect. It's time for manual labor. A whole team of workers with grinding machines, like an army of ants, for hours polishes each blade, bringing its surface to a mirror shine. Any unevenness on the surface of the propeller creates turbulence, which reduces its efficiency and causes destructive cavitation. And the final, most important test for both the shaft and the propeller is balancing. They are installed on a special stand and spun. Sensors detect the slightest vibration caused by imbalance. If there is even the slightest deviation, literally a few grams on a multi-ton part, it is eliminated by drilling tiny holes or removing a thin layer of metal. And only when this steel spine and bronze heart are perfectly balanced and fitted to each other are they ready to go to the port to be connected and begin their long service, silently and invisibly rotating in the dark to move giant ships across the oceans or lift airplanes into the sky. The engine of such a container ship can have a power of over 100,000 horsepower. Imagine the power of 1,000 Ferrari sports cars concentrated in one place. And all this colossal energy is transmitted through a single shaft to a single propeller. The torque on this shaft is so huge that if a lever were attached to it, it could easily lift an entire space shuttle. After final processing, the runout of the shaft over its entire length should not exceed a few hundredths of a millimeter. This is less than the thickness of a human hair. Imagine a perfectly straight line the length of a basketball court. Well, the real shaft does not deviate from this line by more than this microscopic amount, and the balancing of the propeller is generally a jeweler's work. On a 100-ton propeller, an imbalance of a few tens of grams is considered unacceptable. It's like finding and removing 1 grain of sand from the surface of a car. The turbine shaft in a modern jet engine, like the General Electric GE90 on a Boeing 777, is not just a rod. Its length is only a few meters, but it transmits incredible power. And the main thing is the speed of rotation. If a marine propeller makes about 100 revolutions per minute, then the high-pressure turbine shaft in a jet engine rotates at a speed of over 10,000 revolutions per minute. At such speeds, the slightest imbalance turns into a destructive force. Therefore, aviation shafts and turbine discs are balanced with an accuracy of fractions of a gram.